Okay, so this finishes the review of thermodynamics for ideal gas mixtures. The next topic is stoichiometry. Okay, now stoichiometry is the science which deals with calculation of the amount of oxidizer required to burn a given quantity of fuel. Okay, now we have discussed in the beginning that when you want to know, say you are designing a burner, so the burner has a given power rating, so it has to generate so much power, say 2 kilowatt, 5 kilowatts, etc. Then based upon the calorific value of the fuel, you know what is the amount of fuel that has to be supplied here. Okay, so that mass flow rate of the fuel is determined by the power rating of the burner. So I need say x kgs per second of fuel to be supplied to the burner. So that you know. But to oxidize this fuel, what is the mass of oxygen required or oxidizer required? So always we cannot use oxygen. So normally we use air as the oxidizer. Air has 21% of oxygen and 79% of nitrogen by volume. So you have to use this. So how will you calculate the amount of air required for burning the given amount of fuel? Okay, in a flow combustor, that is you are supplying continuously some amount of fuel and it has to be burnt. So you have to continue to supply a given amount of oxidizer also in order to burn this. Okay, so how to calculate this value? That is dealt with stoichiometry here. Okay, now stoichiometry is only theoretical calculation. So what we assume first here is, we assume that the fuel completely burns. Okay, this again you have to recall that we are only considering major products of combustion, that is CO2 and H2O when a hydrocarbon fuel is burnt. Hydrocarbon fuel, all the carbon in it is converted into CO2 and hydrogen is converted into H2O. Okay, so only CO2 and H2O are formed and fuel is not left over. So that is what we are considering. Similarly, all the oxygen should be consumed. So we are trying to calculate only the enough amount of oxygen required for the combustion. That means all the oxygen should be consumed. Okay, so this is a theoretical calculation which will give you the amount of oxygen required. But in practice, you can supply whatever amount you want. Maybe we will supply excess. Okay, to ensure that all the fuel is consumed. Okay, oxidized. Okay, so the complete combustion is assumed here. Okay, so that is the important thing. Now, when I say air, I take only standard atmospheric air, but atmospheric air has lot of impurities and so on. Okay, but standard air I am considering. So standard air is nothing but it has 21% of oxygen and 17% of nitrogen by volume. That is the standard air I take. The other impurities like argon, carbon dioxide, etc., which are usually present in the atmospheric air, is not taken into consideration here. Okay, so that means if I say air, it will contain 21% of oxygen and 17% of nitrogen by volume. Okay, that you have to remember, it's by volume. That's it. Okay, now let us go and do this calculation. Before coming to hydrocarbons, I want to indicate that how will you calculate air? How will you write the number of moles of air? So you can see this. This represents the air. Okay, when I say mole fractions of air, so air has 21% by volume of O2, 79% by volume of N2. Okay, so its volume fraction is known, that is nothing but the mole fraction. So mole fraction of oxygen is 0.21. So I say XO2. Okay. Similarly, N2 is 0.79. Correct? These are mole fractions of the air what we consider. Okay. So now, whether this makes sense, this is 1 mole of oxygen I am saying 1 mole of oxygen. So if 1 mole of oxygen should be present in the air what I take for combustion, how much moles of N2 should be present? That is 3.76. How it comes? 79 by 21. So 0.79 by 0.21. So that will be this. So if I take, if I want 1 mole of oxygen, here this is everything is written in mole terms, kilomoles. So if I want 1 kilomole of oxygen, then I have to have, when I supply air for this, then 3.76 kilomoles of nitrogen also will enter the combustion chamber. Okay. So this is what you have to understand here, so that the mole fractions will be calculated. So here from this you can calculate the mole fraction like this. So here what is this? So XO2 will be equal to 1 by 1 plus 3.76, which will be equal to 0.21 and so on. So you have to recalculate and see. So this is the equation I write. So this is air, this represents air, and this is any hydrocarbon. If I put X equal to 1, Y equal to 4, it is methane. So X general hydrocarbon, CXHY. So C carbon atoms and Y hydrogen atoms are present in this, and I do not know how much air to be supplied basically. So I put A here. So A moles, A kilomoles of air. So I always take 1 kilomole of fuel. So here I do not want to put 1 here. So 1 kilomole of fuel I take, and for combusting it completely I have to supply A kilomoles of oxygen. Okay. Since I supply air, I have to also supply 3.76 kilomoles of nitrogen, and I get the products. Okay. I assume complete combustion. Okay. Two assumptions are made here. The first assumption is complete combustion, where all the X C atoms are converted into CO2 molecules. So X CO2, that means if you say carbon balance, left hand side number of carbon atoms is X, right hand side also C X, you can see in the front. So X atoms are there. Okay, now Y is the number of hydrogen atoms. Now here Y by 2 into H2, that means Y atoms are there, H atoms are present. So I do only the atom balances to get this. Okay, now what will you do with nitrogen? Nitrogen I assume as inert. So the second assumption what I make. Okay, nitrogen is assumed as inert, and then it is good for all practical purposes. So no harm in it. Even if nitrogen reacts with oxygen to form some nitric oxide, they are very minimum, like negligible in this. Even negligible is not good for us. So even if it reacts, we need not even worry about those numbers here for at least calculation of the required amount of air. So I treat nitrogen as inert. So you can see that 3.76 times A kilomoles of nitrogen just appears in the product like this, without having any reaction. So it is inert. So just it comes in the product. So nitrogen is automatically balanced. What is the number of moles of nitrogen in the left hand side? 3.76 times A, and in the right hand side it is 3.76 times A. So now when you do O balance, you will get the value of A as X plus Y by 4. That is it. Okay. So that means when you want to completely burn an hydrocarbon with X C atoms and Y H atoms, then you need number of moles of oxygen equal to X plus Y by 4. Okay. So for methane, X equal to 1, Y equal to 4, then A will be equal to 2. So I can write the equation of for methane as CH4, 1 mole of methane plus 2 moles of air, that is air means O2 is only 1 mole and nitrogen is this, giving 1 carbon atom, so 1 CO2 plus 2 hydrogen, so 2 H2O, 4 hydrogen, so 2 H2O plus 2 times 3.76 times N2. No oxygen will be there, oxygen is fully consumed. Complete combustion, oxygen is fully consumed. Okay. Because you are only trying to find the exact quantity of oxygen required. Okay. Now for hydrogen, so I do not have C now, hydrogen you take H2 and I am combusting hydrogen with air. So A times O2 plus 3.76 N2 giving H2O plus, okay, actually it should be A by 2, okay, A by 2 times O2, because so you need only this, okay, you can also write like this. So A I will just try to correct this. This is A into N2. Okay. So, now you can see x equal to 0 here, y equal to 2. So, A equal to 0.5. Okay. So, here 0.5 times 3.76 times A into N2, that is what you have to write here, 3.76 times into A into N2. Now, A is 0.5, so substitute here. So, this is a mistake here. So, H2 plus A times O2 plus 3.76 N2 giving H2O plus 3.76 times A times N2. So, now you can find this is half. So, you can write the equation as H2 plus half O2 plus 3.76 times N2 giving H2O plus 3.76 by 2 times N2. Okay, so this is the equation you get. Hydrogen combustion with air. Okay, now you determine the number of moles of air required for burning. So, when I say number of moles of air, see, when I say number of moles of oxygen, it is 1. When I say number of moles of nitrogen, it is 3.76. So, the number of moles of air is 1 plus the mixture, no. So, 1, just add the number of moles of oxygen and nitrogen in this. So, number of moles of air is written as 1 plus 3.76 equal to 4.76. Same n equal to n plus n1 plus n2. There are two components. One is oxygen, another one is nitrogen. So, add them. So, n air is 4.76. Okay. So, if you want to supply 1 kilomole of oxygen, you have to supply 4.76 kilomoles of air. Okay. Now, another definition is stoichiometric air fuel ratio is nothing but the mass of the air required to completely burn 1 kg of fuel. Now, we have found what the number of moles required to burn 1 mole of fuel. So, here in this previous slide, 1 mole of fuel requires A moles of oxidizer air. Okay. Now, that is what we have found here, molar basis we have found. Now, we are trying to do ratios in mass basis. Stoichiometric air fuel ratio is mass of air required to burn 1 kg of fuel. Okay. Now, for methane, I will write the equation so that okay. So, this is the equation CH4 plus 2 times O2 plus 3.76 N2 gives CO2 plus 2 H2O plus 2 times 3.76 into N2. Okay. So, this is the equation you have. Now, reactant side you will see 2 into 4.76 total number of moles in air into this is the molecular weight of air, okay, divided by molecular weight of methane. So, this is molecular weight of methane and this is molecular weight of air. Okay. So, how you get this molecular weight of air? 0.21 times 32 plus 0.79 times 28, where 32 is the molecular weight of oxygen and 28 is the molecular weight of nitrogen, and mole fraction of oxygen is 0.21. So, 0.21 times 32 plus 0.79 times 28, that will give the molecular weight of air, and that is 28.84. Okay, molecular weight of methane is 16. So, number of moles of the air is 2 times the number of moles of this each component added together. So, 2 times 4.76 times 2 times 4.76 is the number of moles of air into its molecular weight is 28.84. Okay, that is the mass of the air divided by 1 mole of methane into its molecular weight is 16. So, this is the ratio. So, that means if you want to burn 1 kilogram of methane, you should supply 17.16 kilograms of air theoretically to burn it completely. Okay. So, I have given here, you can see this. Okay. 28.84 is the molecular weight of air, it is calculated like this, and the molecular weight of methane is this. Okay. Now, when you take higher hydrocarbons, okay, straight chain, for example, C4H10 is butane, then heptane and so on. Then what happens is, this is very high, methane 17, but it actually decreases and becomes almost a constant. So, you get say, you can say that for higher hydrocarbons, straight chain hydrocarbons, you will get the stoichiometric air fuel ratio as around 15. That means you need roughly 15 kgs of air to burn 1 kg of hydrocarbon fuel. Okay, you can try to do a calculation and see. Okay. So, now as I told you, we have assumed that nitrogen is inert, but as I told you, in reality where the temperatures are high enough and availability of oxygen is also more, then what happens is the nitric oxide can be formed. NO, NO2, N2O, etc. they can form, but they are not very high in amount. Okay, when compared to CO2 and H2O, they will be not very high. Okay, one more thing what can happen is the temperatures when they exceed say 2000 Kelvin, what happens is CO2 will not remain as CO2, it will break into CO and O2. Okay, so this is called dissociation. So that also can happen. Similarly, still higher temperature than say 2000, it may say 2500 or something, you will see that water vapor also can dissociate to form H2, and some radicals like OH can form, hydroxyl radicals can form, and this means that the products need not be just CO2 and H2O, it can also have all other things. But please understand that theoretical calculation, to calculate the required number of the just required number of oxygen to burn a given amount of fuel, we do the stoichiometry. Okay. So, there is nothing wrong in assuming this is the products, only two or the major products are only formed. Okay. Complete combustion is there, but in actual scenario we will not only use the theoretical air. Okay. We will either do combustion with excess air, or we will do staged combustion. There are multiple stages in the combustion. In one stage we will only supply 80% of the required air, theoretical calculated air, what we call stoichiometric air, 80%, and in another stage we will supply say remaining 20%, and in the later stage we can also supply excess air, say, so that the total air supplied will be more than the stoichiometric air. So, that is also possible. So, the actual air that enters the reaction zone or the combustion chamber can be different than, and it is actually different in several applications than the stoichiometric air. So, based upon this we define what is called an equivalence ratio phi. Here equivalence ratio, which is nothing but the ratio of stoichiometric air fuel ratio, what we calculate by assuming complete combustion, okay, to the actual air fuel ratio which is supplied to the combustion chamber. Okay. So, phi is equal to stoichiometric air fuel ratio divided by the actual air fuel ratio. Okay. Stoichiometric air fuel ratio is the mass of air divided by the mass of the fuel under theoretical conditions, stoichiometric conditions. Actual air fuel ratio is the mass of air actually supplied to the combustion chamber divided by the mass of the fuel. Okay. Now, if they are equal, the phi equal to 1, that means that you are only supplying the stoichiometric air. If P is less than 1, phi is less than 1, then you are supplying the air which is more than the stoichiometric air. That means if you mix fuel and air such that you have more air than required or calculated by the stoichiometric equations, then that is called fuel lean mixture, because fuel is less than what it should be for the stoichiometric mixture. Similarly, if phi is greater than 1, then you will have rich fuel, less air. So, this is very important, equivalence ratio is very important quantity. So, that is what is going to see for any combustion chamber, we will say either we will specify the air supply by using equivalence ratio, or you can say percent theoretical error, which is also dependent on equivalence ratio. Okay, so this is very important. So once you decide the amount of air theoretically to be supplied, then in the actual process we can alter that. So we can also do staged combustion, as I told you, and in one of the stage it may be phi may be greater than 1, in another stage phi may be less than 1, and so on. So total overall the phi may be less than 1, but in the stages we can have our own controls. Okay. Now let us consider N-heptane as the fuel, C7H16. Theoretically, the number of moles of oxygen required to burn 1 kilomole of heptane completely is x plus y by 4, where x equal to 7 here and y is 16. So you will need number of moles of oxygen to be 11. So you can write the equation. See, now let us consider more oxygen supplied. So that means you only want 11 kilomole per kilomole of fuel. Now I supply 13.75 kilomoles instead of 11 kilomoles of oxygen. So, okay, so I supply this. Now if I complete the equation, you can see that when I assume complete combustion, which is actually possible here, then you see that I get O2 in the products. So the rest 13.75 minus 11, the 2.75 appears in the product. Okay, the excess 2.75 kilomole of oxygen is seen in the products. Okay, on the other hand, if less air is supplied, only say 9 moles of oxygen, 9 moles or kilomoles, whatever you can write, of oxygen, then it is not easy to write the equation. So here, when you supply more air, it is very easy to write the equation, because oxygen is considered inert. Again, it does not have much fuel to react with, so it just appears as oxygen in the products. On the other hand, now what I do is, I now consider only less amount of this oxygen. See, 11, I am not supplying 11 kilomoles, I am supplying only 9 kilomoles here. So you see, I do not know what will happen. So let us assume this. See, all the carbon is not going to convert it into CO2, obviously, because you do not have enough oxygen. So some of the carbon is converted to CO2, but some will be converted only to CO because deficiency. Similarly, some of the hydrogen may not burn. We do not know what is true or false, because this A, B, C, D which I put in the right hand side is not just atom balances here. We have to incur other relationships for calculating A, B, C, D here. Okay. So now, but one thumb rule is, hydrogen normally is much highly reactive species than carbon. So what happens is, hydrogen will first try to take all the possible oxygen. So conversion of hydrogen into water vapor will first occur. So then within the available oxygen, the number of moles of CO or CO2 will be decided upon. Okay, but if you starve the mixture with more and more like a fuel and less and lesser oxygen, then you can see hydrogen appearing in the products. So, but it is not easy to complete this reaction. So incomplete combustion occurs, C1H2 formed, but it is not straightforward for us to calculate the values of A, B, C, D in the right hand side of this. Okay. So again, I am taking the same equation for oxygen star combustion. You see that if you have to use what is called a concept of chemical equilibrium, which is dependent on the second law of thermodynamics. Okay, we need, that is what I am saying, that we do not have sufficient data to analyze this. We need temperature, pressure at which these products are going to be present, and based upon that we have to calculate what is called an equilibrium constant, Kp, and for that we need some free energy calculations. Gibbs free energy, G equal to H minus Ts. So entropy will be, so whenever I say entropy, then second law is involved in this. So a second law based property is entropy, and based upon that a derived property is G, Gibbs free energy. So G equal to H minus Ts. Okay, so that will be used. This equation basically is the mechanism of what are the reactants and what are the products, but this equation is not going to occur like this when the fuel is oxidized into products. So we need a lot of elementary equations. So these are the other things which we need to study before addressing the problem of oxygen starved conversion. Okay. So that is what we should understand. So this equation what I have listed here, basically if you write say instead of 9 you can say 11, that is the stoichiometric equation, that is the representation of the overall global reaction. So I say global reaction. Okay. But this global reaction, please understand, it is written in molar basis. Okay. On the other hand, when I say elementary reaction, I will write in molecular basis. Okay. The examples of elementary reactions are this: H2O giving H2 plus half O2. Similarly, CO plus H2O giving CO2 plus H2. So these are all elementary reactions written in molecular basis. I will explain this more when you see the combustion kinetics. But we need to use for your information now, to calculate A, B, C, D, you need to know the temperature and pressure at which the products are. These are products, they are going to be there at what temperature and pressure. Then we need to calculate equilibrium constant Kp based upon the temperature, which depends on the Gibbs free energy. Then we need to use these Kp values on elementary reactions like this, and so CO2. So basically you have to use this. See, for example, very easily you can understand that C balance can be done. There are 4 unknowns here, A, B, C, D. Okay. Now N is already balanced, correct? N is already balanced. So now you have 3 components, C, H, O. It will give 3 equations, correct? So say carbon balance, left hand side 7, right hand side A plus B. So I can write carbon balance as 7 equal to A plus B. So this is equation 1. Then second is H balance 16 equal to here 2C plus 2D, correct? This is equation 2, correct? Then O balance, this is H balance, and this is O balance I will say. O balance gives here 18, left hand side O atoms, it is 2A plus B plus C. Okay. So this is the third equation I have, but 4 unknowns are there. So that is what I am we told that it is not possible for us to solve this. So we have to take one of these equations here, okay, and do the equilibrium calculation in order to find the fourth product. Okay. So whenever you have oxygen star conversion or dissociation, okay, this may not be due to oxygen star conversion. Still we can have 11 here instead of 9, you can have 11, but CO2 can dissociate to form CO and O2. Okay. Similarly, H2O can dissociate to form H2 and O2 and so on. In such case also, the number of unknowns in the right hand side will increase, and we have to invoke the chemical equilibrium approach. So we will see that in the later thing, but I want to just let you know this. When you do a fuel lean combustion, excess oxygen, then it is easy to write the equations like this, assuming again the complete combustion, which is possible here. When there is a oxygen star conversion, we need to use chemical equilibrium to close the loop. Okay, that is what I have explained here. To calculate the values of A to D, 4 equations are required. Atom balance CHO gives 3 equations, and the fourth equation is got by chemical equilibrium. Okay. Now for this particular case, we can use this equation. So I have shown some 3 elementary equations in this slide. CO2 giving CO plus half O2, H2O giving H2 plus half O2, but you cannot use you need only one more equation to solve, for which you have to find the Kp value and plug it on. Okay. So what equation you will choose? Let us choose this, because this has all the species involved in this: CO2, CO, H2O and H2. So CO2, CO, H2O and H2, all these 4 species are there in this. So if you use this equation, then we can have one more equation which has A, B, C, D in it. Okay. So, how will you do it? We will explain later. So, normally what we do is, we will invoke this equation, elementary equation. This is called water gas shift reaction. Okay. So, this I will explain again more later. So, this equation you invoke, find Kp of that, write an equation in terms of A, B, C, D, but unlike these atom balance equations, which are linear equations, when you use Kp for this, you get a non-linear equation. So, if one of the equations in the set is non-linear, then you have to solve a set of non-linear equations to find the values of A, B and C, D. So, in this way, calculating the products are not so straightforward. Okay, so that is what I want to. So, this aspect will be dealt in chemical equilibrium section later.